What did we do 2 weeks ago? We started with the filters, right? There was a long discussion on filters. Oh yeah, I remember now. It's the matching method, right? We deliberately want to mismatch between input impedance to output impedance, right? If you are designing filters. So we don't want maximum power to transfer from input to output. So that's why the mismatching method is important here. Okay, so that's and then we also looked at the damping uh, component of the filter, right? Which is important as well. You don't want the filter to have very low damping because that would be dangerous to um, just the performance of the filter, right? Overall performance of the filter. You have a gain in sort of attenuation, right? And then also we'll discuss this today. This also make it risky for stability of the system, right? We'll discuss that today. So it has to do with performance of the filter in terms of blocking the signals as well as stability of the power supplies, right? That's why the damping factor of the filter is also significant, right? And we talked about different ways of introducing damping, right? From good method to the bad method, right? Like this one is probably the worst method to do damping, right? When you have parallel resistance across the capacitor, right? Because basically you have a, what do you call it, a bleeding resistor, right? So this is always consume power, basically, right? And these are the transfer function, gain transfer function with the damping, and then the output impedance of the filter with the damping. All right, let's proceed with the next topic. I mentioned earlier about stability, right? Um, let's have a look at how filters affect stability, which is something that's I don't think any of you've heard before, right? That a filter on the input. This is input, okay? This is not output. Output filter makes sense, right? It affects stability because that's when that's where the loop, right, or output filter is inside the control loop, right? So it makes sense that the output filter affects stability. But imagine the input filter, right? Input filter is not part of the loop, um, the control loop, I should say. It's not part of the control loop. So how is that affecting um, stability? So that's what we're trying to understand through this section. Well, first of all, what's unique about power supply is that in steady state, when it reaches steady state condition, meaning output voltage is constant, output current is constant, right? So you have um, power supply, right? And then you have constant output voltage, and then constant output current, right? If you have constant both current and voltage on the output side, that means P out is also constant, right? So P out is also constant. Okay, and then per given input voltage, right? If P out is constant, P in will also be constant, right? So I in is constant as well, right? That's steady state, right? But what happens if I do this, right? Again, the output parameters are all constant, right? So these are all constant. What happens if I do this? What happens if the input voltage drops? Right? The input voltage drops, right? What's going to happen with I in? Well, because output power is constant, that means it would demand constant input power, right? If input voltage decreases, right, whatever reason, that means I in would have to increase, right? So this is unique because it means that the input impedance of the power supply is actually negative, right? So it has a negative input impedance. Um, the next page shows you the equation, right? So Z in is equal to delta V in over delta I in, right? So the input impedance, basically looking into the power supply right there, Z in, right, is equal to the change in the input voltage divided by the change in the input current, right? The ratio of the change in input voltage to the change in the input current gives you input impedance, right? So mathematically, delta V in could be expressed in terms of V in and I in. The change of input voltage can be expressed as follows: V in 2 minus V in 1, right? The new value minus the initial value, and then delta I in is equal to the current value after the change and the initial value before the change, right? What did I say earlier? I said that V in drops, right? V in decreases. So V in decreases, right? Which causes I in to increase, right? Why again? Because output power is constant, right? Output power is constant, therefore input power is constant. To maintain constant input power, when V in decreases, I in has to increase. You agree with that statement? All right. Then V in decreases, that means V in 2 is less than V in 1, right? And then I in 2 must be larger than I in 1, right? Go ahead and put it into this equation right here, and what do you get? You get negative sign, right? Negative value on the numerator, right? Because again, V in 2 is less than V in 1, so that's negative, right? And then I in 2 is larger than I in 1, so therefore it's positive. Negative divided by positive gives you negative, right? So you can see clearly from that simple mathematical proof that the input impedance of the power supply is actually negative. Right? Again, it's unique, right? That way. Okay. We'll come back to that. So hopefully that proves or that convinces, I'm able to convince you that that the input impedance of a power supply is actually negative, right? Okay, let's look at the modeling of the input impedance, right? You could model the input impedance of a power supply in general to be this type, right? Or can be represented by this circuit right here, where you have a transformer to model the the duty cycle of the input to the output, right? So depending on the type of topology, whether or not you have a buck converter, boost converter, or buck boost, that would determine the quote unquote, transformer uh, model of this power supply, right? And then you have the output filters and the load, right? That's the load right there. That's the typical output filters, right? Output filter of a topology, any topology, right? Where you have the L value, that's the inductance value of the output filter. RE would be the DC resistance of the inductor. And then you have the capacitor by itself, right? And for this model, we ignore ESR for now, right? Okay, that's the model of getting the input impedance, basically. Again, if you look at the turns ratio here, it's 1 to mu, where mu, right, is if it's continuous conduction mode. If it's a buck converter, that mu becomes D, duty cycle. If it's a boost, 1 over 1 minus D. If it's a buck boost, it's D over 1 minus D, right? As you learned from EE410, right? That's a continuous conduction mode transfer function, right? For a buck, V out over V in is equal to duty cycle, right? For boosts, V out over V in is, what is it? 1 over 1 minus D. And for a buck boost, right, which is a combination of V out over V in will be minus D over 1 minus D, right? And over here, keep in mind, we are looking at impedance, magnitude of impedance. So therefore, actually not magnitude, sorry, just the impedance as Z in, right? So therefore, the minus doesn't matter, right? We're just looking at impedance, input impedance. So that's why you don't see the negative sign over here, right? Okay. Any questions? Right, so then converters input impedance and its frequency response. If you, again, by knowing the turns ratio, right, of the converter per given topology, then input impedance, right, again, by knowing the transformer turns ratio, right? Now, I need to mention this one more time. This doesn't mean that there is a transformer. This is just to model, okay? Just to model the conversion ratio between input and output, right? It doesn't mean that it's a physical transformer, okay? What if there is a physical transformer? Then, oh, I forgot to mention that. All right, it's actually right here. If there is a physical transformer, such as push, pull, flyback, and forward, then you just divide the whole thing by n, right? For example, this becomes d divided by n. Is that what I said here? Then the effective transfer of the conceptual is divided by n, yes. So this becomes 1 over 1 minus d divided by n, right? And then d 1 minus d divided by n, right? In case there is a physical transformer, right? Then you just add n. What is n again? That's the trans ratio, right? V2 over V1. Or sorry, N2 over N1. Okay. All right, let's go back. I just want to make sure that that's clear. So knowing that, right, if I know the model there, the transformer is already taken into account, then you see the input impedance on the secondary side of the transformer, you'll see just this portion right here, right? Okay. Any questions so far? So let's derive the input impedance equation. Okay, that's what I have here. I have derived the equation for that input impedance. It's a long algebra, as you can see. I won't go through it in detail, but you can see it's just finding, again, the equation for the input impedance, which consists of series combination of L and RE in series with parallel combination of RL and C, right? That's what I did right here. And I'll let you check my algebra. Right, that's this right here. And at the end, I have this equation for Z in, but I don't like this format. The reason being, I want Z in to, I want to express Z in terms of real part of Z in plus the imaginary part of Z in. Right. In this equation, I mean, I could see some, right? Like for example, here, that's the real part of Z in. I know that part is the imaginary part of Z in. But what about this part? Which part does this belong to, right? So it's not clear because you have a complex number at the denominator. So how do I get a clear separation between the real part of the input impedance from the imaginary part of the impedance? Well, I could multiply top and bottom by the what do you call it, complex conjugate, right? So if you multiply top and bottom by the complex conjugate of this, then you get rid of the imaginary part on the denominator. So if you do this like that, then you get this right here. Notice as soon as I do that, there is no J anymore on the denominator, right? There's no J anymore. So that's good because then I could break this term down into two, right? RL minus this term. So I can break it down into RL over the whole thing, which is right here, and j omega RL squares, j omega RL square times C, right, on the other term, and then divided by the same denominator. See that? So that's the process of what do you call it? Separating real part from imaginary part for a term that has complex number at the denominator. I just simply multiply top and bottom by complex conjugate. Now, in this equation right here, I could clearly see which part of the input impedance would be the real parts, which ones would be the imaginary part, right? That's real part, that's real part, and that's imaginary part, that's imaginary part, right? How do I know that? That's a J right there, and there's a J right here, right? So that's what I did right here. I once I break it down into real and imaginary parts, then I group together the real part and the imaginary part. Now I can clearly see the real part of the impedance and the imaginary part of the impedance. Any question on this? Why is it important for us to do this, right? In case you're wondering, why is it important for us to separate the two, real part from imaginary part? Because one of the things that you could do when you do the analysis of the transfer function, including complex numbers, is that by separating it into two components like this, then you could also find resonant frequencies, right? If you ever need to find resonant frequency of a transfer function, of a filter, of a circuit that has energy storage components, then do this, right? Break it down into real and imaginary parts. And then we know from EE212, right, that resonance, right, occurs when what? Occurs when the imaginary part of Z is equal to 0, or the imaginary part of admittance is also equal to 0, right? So resonant condition occurs when either the imaginary part of impedance is equal to 0 or the imaginary part of the admittance is equal to 0, either one, right? So by setting up the input impedance equation this way, right, then I know how to get omega C, right? Simply by setting this equation right here, setting this term right here to be equal to 0, and then solve for omega. Right? When you solve for omega, that omega right there is the resonant frequency of the circuit. Make sense? All right. Any question on this? All right. So then, well, before I go there, but just give you a heads up, right? That's why breaking it down into two components would be important for filter input impedance of a filter, as an example, right? Okay, so we can then know the resonant frequency of that filter. But before we do that, let's look at what happens with the filter at low frequencies. We're doing frequency analysis right now. When omega is equal to 0, so at low frequencies, right, represented by omega equals to 0, go ahead and plug in omega equals to 0 to this equation right here. What do you get? You get the whole thing reduces to approximately equal to RE over RL. Okay. Any question on that one? So that's what happens at low frequencies. Does that make sense though? Well, our filter looks like this, right? Our filter looks like, oops. Right, like this. L, R, E, L, C, right? When omega is equal to 0, what happens with L? L becomes like a sword, right? This becomes like a sword. What happens to the C, to the capacitor? Acts like an open, right? If that is the case, then what is input impedance equal to? Well, that's a sword, that's an open. So input impedance becomes just a series combination of RE and RL, right? Okay. Any questions on this? So this is in agreement with we were to do it using circuit analysis, right? Okay. What at high frequencies? At high frequencies, represented by infinity, omega equals to infinity. Once you plug in omega equals to infinity to the transfer function to the input impedance equation up here again, right? Go ahead and plug in omega equals to infinity. Then you get approximately equal to RE plus j omega L. Let's see if that makes sense. RE plus j omega L. Again, we have the same filter circuit, right? Like this. RE is right here, L is right here, C is right here. When omega is equal to infinity, what happens with the capacitor? It becomes a short, right? Becomes a short, right? Now this is tricky because omega equals to infinity means this looks like an open, right? But in the process of going to infinity, right, whereas you are increasing the frequency, right, the series combination of RE and L becomes the most dominant components, right? RL is practically out of the picture because being sorted by C. So as you are increasing the frequency, these two becomes more and more dominant, right? So at higher frequencies, right, Z in is approximately equal to RE plus j omega L. Of course, when omega is equal to infinity, this becomes open, right? Oops, this becomes, oh gosh, how do I do that? No, I don't know. I don't know if I can do that. This becomes open, of course, right? If that becomes open, then output is equal to zero, basically, right? I know, not zero, sorry. Input impedance becomes, what is that? It just becomes infinity, right? So becomes infinity if omega is equal to infinity. But again, in the process of sweeping the frequency to higher frequencies, you can see that L and RE becomes more and more dominant, right? That's why at higher frequencies, the most dominant components would be RE and L, whereas at lower frequencies, the most dominant two components would be RE and RL. Okay. Does it make sense or no? Oh, all right. Okay, so that's at higher frequencies, right? How about at resonant frequency? Because we have two energy we have two energy storage components, right? Right here, L and C. So therefore, there is a frequency, there is a possibility that at a certain frequency, we call it resonant frequency, the two cancels, right? The two cancel each other. So that's why you need the equation that shows you the real part and the imaginary part, right? So as I said earlier, man, I don't like this scrolling thing. Hang on. Right, there you go. What is going on here? Hang on. At resonant frequency, there you go. At resonant frequency, imaginary part of the impedance goes to zero, right? So this whole thing right here, uh, this whole thing right here, by applying the definition, this whole thing right here becomes zero, equals to zero, right? That's what I did right here. Right. That's what I did right here. See this? And I've already derived this for you. Again, I won't go through the algebra in details, but at the end, I get omega naught square is equal to this. Or in other words, omega naught is equal to square root of this term, right? Let's call it A. It's going to be square root of A. Right? But I keep it at omega naught square. That's what I'm plugging in the next equation right here. Right. So here's the, once I get omega naught square or omega naught, right? Then I go back to the input impedance equation. Remember, input impedance has real part and imaginary part, right? Right. But at resonant frequencies, at omega equals to omega naught, this goes away. So input impedance becomes just the real part. Agree? Yes. So that's why the next step, what I did was I plug in omega naught that I found earlier, right here, and then plug it into Z in equation without the imaginary part. So only the real part. See that? Only the real part. And then it has omega naught square. That's why I was keeping omega naught square equation and just plug in the omega naught square equation here, right here. Right? That's what I have right there. And at the end, I have the impedance, the input impedance at resonant frequency to be equal to this equation right here. Okay. So now I have three different values, right? To summarize, right? Z in at low frequencies, low omega, that was equal to RE, or approximately equal to RE plus RL. Yes. And then Z in at higher frequencies, that was approximately equal to, what was it? RE plus J omega L. Yes. And then Z in at resonant frequencies, that's equal to RE plus that equation right there. 1 over RL, L over C. Just to summarize, those are the three critical points, right? That we need to know out of out of the input impedance of the power supply. And I simulated this, right? Just to prove this point, right? I simulated this. Right here, that's the circuit, right? I sweep the frequency. So I perform frequency analysis in ORCAD, and RE is 0.1. L out is 10 micro, just for the sake of example. So I pick these values, and then C out is M times 10 micro. Right? Where M is equal to, what is M equal to? Right here. This is actually M. Can you fix this in your book? This is actually M. So M is the ratio of, right there, the ratio of capacitor and inductor. You can see from here. So change it to M because that would be confusing, right? If you use N again, we can get confused with the turns ratio, right? So just change it to M, where M is equal to, what is it again? CO over LO, looks like, right? From this. Okay, so this is M is equal to 1. This is M equals to 10. This is M equals to 100. Right. So I plotted the input impedance at 3 different values of M, right? So depending on how big the capacitance is with respect to the inductor, you have different frequency response of the input impedance, right? Now look at just focus on one. Let's focus on the solid line right here. Okay. What did we say earlier? At lower frequencies, what is the input impedance equal to? Ah, come on, this scrolling thing. At lower frequencies is equal to RE or plus RL, right? So let's just do that here. RE plus RL. That's a constant value, isn't it? So at lower frequencies, right here, right, the value here should be close to RE plus RL. Is that the case here? Yeah, you see, RE is 0.1, RL is 1. So it's about 1.1, right? You can see it's, the flat line right there is slightly above 1, right? So right here, 1.1 ohms at low frequencies, right? And then what else did we say? We said that at higher frequencies, right, the impedance, the input impedance is RE plus j omega L, right? So that's what do you call it? That's a line with a slope of 20 dB per decade, right? Right here. So it's a slope right here. Yeah, as you can see, it's a slope, right? RE plus j omega L. So as L becomes, sorry, as omega is increased, of course, the line goes up, right, accordingly. Right? It's like a straight line of, it's like a line equation, basically, right? This is equal to 0.1 plus j 10 micro omega, right? So as omega increases, the magnitude also increases, right? And what did I say last time, earlier? That when omega is equal to infinity, then the magnitude is also goes to infinity, right? Look at this filter, right? If omega is equal to infinity, what happens with the input impedance? Well, inductor becomes open, right? And then R doesn't matter, RL doesn't matter. Capacitor becomes a short. So if you look into the circuit, what is the input impedance there? Infinity, right? Open. That's the proof right there, right? As omega keeps increasing, the impedance becomes very high, right? Make sense so far? And then lastly, at resonance, right? At resonance, what was the value again? I do not remember. Right here, RE plus 1 over RL times L over C. No, I have the equation, calculation right here. I have the calculation right here. Again, this is M. Please change it. Right. So you can see at resonant frequency at omega naught, when M is equal to 1, then I just plug in, right, those values for the resonant frequency. It turns out to be for M is equal to 1 is 1.1 ohms. So let's check if it's the case. When M is equal to 1 is 1.1 ohms right here. And it is 1.1 ohms. What is it? It's like a negative side. That's a negative minus, sorry, hang on. 1.1 ohms. Does it look like it's 1. It doesn't look like it's 1.1 ohms, huh? The other one, if you look at M equals to 10 and M equals to 100, M equals to 10 is 0.2, M equals to 100 is 0.11, right? So you can see that one makes sense. Those make sense, right? 0.2, that's below 1. So this is 0.1, right? That's 0.1, that's 1. So when M is equal to 10 is 0.2. So that looks correct to me. That's about 0.2. This one is about 0.11. Yes, I agree, right? But that one, this last one, that one doesn't look like it's 1.1. It looks like it's 0.9 or something, right? You agree with that? That doesn't look like 1.1. Did I calculate it wrong here? I might. RE is 0.1. RL is 1. L of C is L of C is equal to 1. Is that why? It is true. It is right. So I'm not sure about M equals to 1 here. Why is it the value does not correspond well? That looks like it's less than 1. So I'm not sure yet why at M equals to 1, the value of the input impedance does not match with the calculated value. There might be some unique thing about M equals to 1. I'm not sure yet. But look, if you look at the other ones, though, they match, right? They match nicely, right? They agree. The values agree with the graph that we have earlier, right, on the previous page. And so I'm not sure again. I have to look into it. Maybe that's not a good example to use. 10 micro and another 10 micro. I'm not sure why though. Right? All right. Any questions besides M equals to 1, which is still a question mark? But other than that, the other values looks good. Any questions? This still bugs me. All right.
I have a question, actually. Can you hear me?
Yes.
With regards to like stability, would we have like better stability at the lower frequencies or higher frequencies, or would it be like at the
Yeah, no, not yet. We haven't got into stability yet. Right now, we're still looking at the input impedance of the power supply. In order to assess stability, we also have to know output impedance of the output filter. Has to be a combination of both.
Gotcha. Okay.
Right? So yeah, you'll see later on.
Okay, sounds good.
Okay, thank you. All right, so those values agree except for M equals to 1. Again, I'm still not sure why. All right, and then what is this next? To summarize, based on the canonical model, converter's input impedance is the load impedance R of L reflected through the transformer to the input. Recall also that the input impedance is negative, right? And then again, if you reflect everything to the primary side, right? Over here, when we derive this equation, we reflect everything to the secondary side, right? That's why you don't see the transformer. Let me go back. See this? There's no transformer here. But if you reflect everything to the primary side of the transformer, then the equation would be this equation right here. You just include the mu, right? The turns ratio, right? Okay, and the rest will be the same. You just divide it by the turns ratio square, right? If you reflect it to the primary side, as you learned from 212, right? So I won't go through this. It's just the same equation as the previous ones, except you divide it by mu square. And mu again depends on the topology, right? If it's a buck with a well, not a buck, but if let's say this is a push pull or forward, that's going to be d divided by n. If it's a buck, it's going to be just d without the n, right? And so on and so forth, right? So here's the, we'll call it, here's the input impedance plot if you include the turns ratio, right? The duty cycle basically. So just like you see here, right? It's actually the same as this. It starts off from flat value, RE plus RL, and then it goes down, right? And I forgot to mention, this is a proof that this is a negative impedance, right? That's the proof that it could gives you negative impedance right here. Right? At these frequencies, it goes to negative, right? The value is if you do log scale, it will be negative. It's the same shape, right? It doesn't matter if you add the duty ratio or not, it will still be the same shape, right? So starting from flat, and then it reaches its minimum at resonant frequency, and then it goes up as you increase the frequency, right? All right, now stability, right? How can we relate input filter with stability? Here it is, right here. Okay, consider a load having a negative dynamic input impedance, such as power supply. So let's say that this is the source impedance of the power supply, and here's the load impedance of the power supply. Keep in mind that this right here, from here to here, so watch from here to here, right? This may include the output filter, the one that we just did earlier, right? Remember this model, right? So not just the load by itself, but the entire filter as well, right? And we know that it is a negative impedance, right? That this input impedance is negative input impedance, right? Now, that's why I put minus RL right there. All right, so what's saying here? Okay, so here's the source impedance. Here's the input impedance to the power supply. Here's the input impedance to the power supply. Right. And then what happens if, okay, what happens if on the next page, when the source voltage Vs is lowered slightly, then V in goes down and the load demands more current, right? Let's go back. Let's redraw it over here. That, right? This is R of S, this is R of, what is it? I forgot. Of L, Z of L. Z of S, this is Z of L, right? And here's the input impedance, right? V in into the power supply, and here's the source of the power supply, right? And what did I say here? When the source voltage Vs is lowered slightly, so right here is lowered, so it decreases, then V in goes down, right? Accordingly, right? As you can see, that's a voltage divider, so V in goes down. So as Vs goes down, V in goes down, right? This increase causes an increase I times R of S. Oh, sorry. Then V in goes down and the load demands more current due to the negative impedance, right? So because this is negative impedance, remember earlier, if V in goes down, that means I in has to go up, right? For the constant power, right? When V in goes down, because the source voltage goes down, then the I in input current to the power supply becomes higher. Right? If I in becomes higher, guess what happens to this voltage across ZS? The drop, right? I in times GS becomes higher, wouldn't it? Right? That's what I put right here. When the source voltage Vs is lowered slightly, then V in goes down, right? And the load demands more current due to the negative impedance. This increase causes an increase I times R, right? Right here, R of S, the source across the source impedance, further lowering the voltage seen by the load, right? So we have a dilemma, we have a problem here, right? As you are decreasing Vs, V in decreases. Again, don't forget, okay, V in is the input to the power supply. Vs is the source of the power supply, right? And then I in goes up, right? When I in goes up, then the drop across ZS goes up again as well. By KVL, right? This is V across ZS. by KVL, if VZS increases, that means V in is going to be decreasing more, right? As you know, Vs is equal to VZS plus V in, right? So if VZS keeps increasing, right, because current increases, that would force V in to decrease even more, right? So that's the problem we're having here, right? Let me go to this blank page, right? Oops, let me draw it this way. Let's say this is our power supply, right? This is our power supply, right? And then we already learned earlier, right, that and in steady state, right, if I out is constant, V out is constant, that means P out is constant, right? If P out is constant, that means P in is constant, right? Then what happens if I now connect this to a source, right? The actual source that has impedance, like this. That's what's happening now, okay? Just to make sure you're clear on this, right? So actually I'm connecting the input terminal of the power supply to a source that has source impedance, right? So now we have, let's call it Z. Right? The voltage across this impedance is VZS, right? So what happens when V in decreases? Well, V in has to decrease to compensate, not to compensate, sorry, based on KVL, right? Or based on a voltage divider, basically, right? V in has to decrease accordingly, but that would increase I in. If I in increases, that means voltage drop across ZS increases. If voltage across ZS increases, then with the decreased value of Vs, V in will also have to decrease more. Right? You see the problem here, hopefully? Does that make sense? Or do you have any question on this? No? So you see the problem here, right? As soon as Vs decreases, V in decreases, I in increases, drops across ZS increases, which in turn makes V in even is decreasing more, is even decreasing more, right? So that's not good, right? Because then I in keeps increasing. When V in keeps decreasing, I in keeps increasing. When I in keeps increasing, guess what? Voltage across impedance keeps increasing as well. So that now we have a chain reaction, right? You see this? And this doesn't stop if what? If ZS is significant enough compared to the input impedance of the power supply, right? So in that picture, I basically I model all of this as a single resistor. If I go back to here, see that I model the whole thing with just a single resistor. But keep in mind, this is the input impedance of the power supply, right? So we're going to have a problem here, like chain reaction type of problem, in that voltage at the input of the power supply will not be able to recover, right, from the decreasing value of Vs, right? Just a single event of decreasing Vs gives V in continuous decreasing, right, of the value to the point that the output voltage, the actual output voltage becomes zero, right? Because the power supply gives up, right? Because the input voltage keeps decreasing, that means duty cycle has to go up higher and higher and higher until it reaches the limit, right, of the duty cycle, right? Remember, duty cycle has a limit of 1, right? In reality, it's going to be maybe around 0.99, I don't know, 95 or something, right? So once the duty cycle hits the limit, because V in over here keeps decreasing, then it would give up, right? Because V in keeps decreasing more, and then the controller is out of the regulation, and finally it gives up, and output voltage becomes 0. So this, I hope you understand the problem first, though. Is that are there any questions on this? So this problem it occurs if the impedance right here, the source impedance, is significantly, not significantly, is higher than the input impedance of the power supply. Right? So if the source impedance, right, is larger than the input impedance, right? This is input impedance of the power supply, impedance of the power supply, then V in will not be able to recover. Right? However, if ZS is less than ZL, then for sure this is going to be okay, right? It's gonna recover. The change in the drop, the decreasing rate of the V in will be much less than how do I say it? The decreasing rate of no, not that way. The increasing rate of VZS, if R of S is smaller than R of L, the increasing rate of voltage across ZS will be much, much slower than the decreasing rate of the B in, right? So that would make it more stable. Let me repeat what I said. The increasing rate, of VZS, if it's much less than the decreasing rate of V in, then we'll be okay, right? Then V in should be able to recover. The problem is it occurs when the increasing rate is faster than the decreasing rate, right? So V in cannot keep up. Basically, the duty cycle on the converter cannot keep up with the increasing rate of VZS. Does that make sense? All right. Okay. So that's the problem with this scenario, right? If you have source impedance, right, connected to a power supply, and the impedance of the source impedance is significantly or is higher than the input impedance of the power supply, then this oscillation may occur, right? The instability may occur. Now, what does it have anything to do with filter? All we did so far, right? We took a look at the impedance of the filter, right? The output impedance, the output impedance, or the gain of the filter, right? Or the output impedance of the filter. That's what we did 2 weeks ago. And then we look at the input impedance of the power supply, right? Am I right? So we already looked at the input filter and the input impedance of the power supply. And then Z out of filter, right there. So then my question is, what does this have anything to do with filter? A lot, right? Remember I said earlier that this is source impedance, right? If source impedance is smaller than input impedance, then we'll be fine, right? And in I would say in many cases, almost all maybe, right? The source impedance will be smaller than input impedance of the power supply, right? Source impedance should be small anyways, right? If you have a big source impedance, then you have problem with the source, right? You have a lot of losses basically, right? So in practice, in real world, source impedance will be small anyways. However, that's not what we have, right? In power supply, we don't have this, right? We don't have. I'm going to draw again. What we have in power supply is that we don't just have this. source, right? And then the source impedance, and then we connect straight to the power supply, right? Or to, buck converter or boost converter. That's not what we do in real world, right? What do we do in real world? What's missing from here? Anybody?
An input capacitor, an
Input filter. Yes, exactly. Input filter. That's what we're missing, right? So in reality, that's what we put in between the two. Input filter. That could cause a problem, right? Why? Because input filter has impedance,
Negative
right?
impedance, yeah.
No, the negative impedance right here. Sorry.
Sorry.
Yeah, that's the negative impedance right here. The filter itself doesn't have negative impedance, right? But the input impedance of the power supply is negative, right? So now what you have is this. What you have is the source impedance, and then filter and C in of the power supply, which is a negative, right? There, that's what we have. You see a problem now? You see the problem now? The source by itself, yes, it's small, but look at filter in series with the source impedance, right? So the whole thing, the combination of the two, now acts like a big Z source, right? If that is the case, then if we're not careful, then the problem that I tried to explain earlier, right, with going back and forth, right, this one, oh, what is it over here? This problem right here will occur, right? The oscillation, right, between VZS and Vin, VZS, Vin, right? They're trying to keep up with each other, right? That would occur if the filter output impedance is significant, right, compared to or comparable with the input impedance of the power supply. Does that make sense? Okay. Now, this is what Professor, what is his name, Middlebrook discovered, right? Is that right here you have the output impedance of the filter, right? This is input filter. Oh, sorry, this is input filter. And there's the source impedance. The combination of both gives you source impedance, right? And the frequency response of this filter, right, at low frequencies, similar to the input impedance of the power supply. So don't get this mixed up, okay? This is output impedance of the input filter. Output, Z out of input filter. Right, so if looking back into the source, right, if you have filters, input filter, at omega equals to 0, what happens? You have RS plus RF right here, right? Low frequencies, you have RS plus RF. High frequencies, you have open here, you have a short there, right? What is it then? Well, if it's high frequencies, then the circuit becomes like this. And you're looking at a sword. You're looking at a sword, right? So what is the impedance of a sword? Very small, right? 0. That's why it goes down, right, at high frequencies. At resonance, right, the equation is Q squared times RS plus RF. Again, you can, I don't think I have derived the equation for the resonant frequency, but you could do the same thing as I did earlier with input impedance of a power supply with Z in of the power supply. What do? You express Z source in terms of real part and imaginary part, right? And then you apply imaginary part concept of resonance, imaginary part of the Z source must equal to 0, right? And then you find omega, which is equal to omega naught, right? And then plug it back into the real part, right? And that should give you this equation right here. So at resonant frequency, you have a peaking effect, basically, right? Depending on the Q of the filter. See that? All right, so now we have two different plots. One from the output impedance of the filter, which is right here, and the other one from the input impedance of the power supply, which is right here, right there. Okay, so keep in mind that one is pointing up, the other one is pointing down, right? The one from the filter, the output impedance of the input filter goes like this, right? But the input impedance of the power supply goes down this way, right? Okay. Any questions so far? All right, so then how do you define the stability here, right? Now that you know the interaction between input filter and output filter, sorry, input filter and the output impedance of the input filter and the input impedance of the power supply, right? Let me write it down so you won't forget. Output impedance, because it gets confusing, of input filter versus input impedance of input of power supply. There you go. Right. And keep in mind, this is the one that has the negative impedance. All right. Now, as discussed previously, the source impedance must be less than the magnitude of the negative load impedance in order to avoid power supply instability, as I said earlier, right? Input impedance also reaches its minimum value at resonant frequency of the filter, right? So if you look at the input impedance, this one, right? Again, the shape looks like this. Right? It reaches minimum value at resonance. For input filter, reaches maximum at resonance. This is at resonance. It's the opposite. The following figure illustrates the worst case scenario where input filter output impedance, high Q, has resonant frequency close to that of the input impedance of the converter, right? This presents an unstable system since Z source will be less than Z load. Remember what I said earlier, right? If the magnitude of the impedance of the input to the converter is less than the magnitude of the impedance of the input filter, then we have a problem, right? So this could be a problem right here. Imagine if you overlay the two plots, right? This one is from where? That one is from the input impedance, right? And this other one is from output impedance of the filter, right here, Z source, right? Again, I'm going to draw this. This is ZL or Z in, negative Z in. Here is Z source, okay? Now, if they overlap like this, that's not good, right? Because if they overlap, watch. If I zoom in, what is the condition for instability again? If Z in magnitude is less than Z source, right? Then we have problem. This is not good, right? So what if I zoom in? If they overlap, if they happen to be overlapping like this, right? See what happens here between here and here? You can see that the ZS, right, which is the blue right here, that's ZS, right? ZS is larger than the red, larger than Z in. That's not good, right? That's not good. Right. So now we have unstable system, right? Because of this, right? You have a negative damping basically. Right? Make sense? So therefore, when you add the filter, as soon as you add the filter, meaning you're affecting the Z source by adding the filter, make sure that um, the frequency response of the input filter does not overlap with the frequency response of the input impedance of the power supply, right? So basically you are adding this plot. By adding input filter, you're adding this plot. Make sure when you do that by adding the filter, make sure when you do that, the peak of the filter does not coincide or overlap with plot of input impedance, such as this, for example. So to avoid instability, it is important to keep the peak output impedance of the filter below the input impedance of the converter, right here, such as this, right? So this is fine, right? What's not fine is if you design a filter that does that, and that's not fine. Then you have instability, right? I have to do this slowly because this is a quite a complex, concept, right? It could be confusing. That's why if you didn't pay attention, I'm sure you you get lost right now, right? Because you have to understand the difference between input impedance of the power supply versus output impedance of the filter, right? And that's how we can determine instability, right? That's how we can understand the effect of the filter to the stability of the power supply. Are there any questions? So this next one is just summarizing when you do have to use input filter, right? What will be the goals? Minimize the peaking, right? Because if you happens to have a very low Q filter, then this, even though it's away, but if the Q is very high, it may overlap, right? Like this. Right? So make sure that the Q point is not too high, or minimize the peaking, right? That way you could avoid the overlapping between the two responses. Right? Maximize attenuation. Yeah, that makes sense, right? If you have a filter, definitely you want to attenuate more, right? Instead of this, maybe this way, right? So you attenuate more, right? So that makes sense, right? What else? Yeah, I'll let you read all of these. Yeah, and then also it has to do with the slope. I forgot. Yeah. Well, in fact, by doing this, I actually did increase the slope, right? So instead of first order system, you can do second order system, third order system, right? Like this. But notice the Q gets higher. If you do that, right? The Q gets higher. So yeah, just make sure that when you do this, there's always a trade-off, right? Increasing order by keeping the same peak, that would make Q get higher and higher, right? Minimize size, weight, and cost, right? That's another goals for the filter. And of course, avoid the overlapping, right? Avoid the overlapping of the two plots, right? You need to make sure that these two don't overlap, right? All right. From a system point of view, right? Choose topology to minimize emissions. That way you can just put minimum amount of filtering, right? So minimize the input filter requirements if you choose topology that does not emit, that much emissions, right? Topology such as boost, like inductor driven at the input type of topology, that would minimize emissions. A buck converter, that would be a bad one, right? Boost converter looks like this. For those of you who have not taken EE410, right? So at the input, there's already a inductor for a boost. Inherently, there's an inductor in a boost topology at the input. That would minimize the amount of EMI reflected back to the source, right? It's being filtered by this inductor, right? But a buck is different. A buck has a switch at the input like this, right? So at the input, the current looks like this, right? So you have turning on, off, right? The input current is on and off, right? Basically discontinuous. So this puts back some EMI back to the source, right? So here you have to have some kind of filtering, right? The worst one is one that gives a current back during off time, right? At least for a buck converter, if you look at buck converter, during off time, this is on, off, right? During on time, yes, it reflects some noise back to the source. During off time, there is no current, right? So the source is fine because there's no current anyways. The worst topology in terms of EMI at the input, that happens when, for example, if during the off time, instead of doing this, it does this. And you've seen it, right? If you took EE410, you actually seen this topology before, right? So even during off time, it sends some current back, this continuous current back to the source, right? That's another EMI. So you have EMI during on time, and you have EMI during off time, right? You recall what topology that would be? It's called single switch forward, right? Do I have it here somewhere? Yeah, right here. The worst topology are the ones which feed current back out to the filter during off time of the switch, such as forward converter, right? So if you took port 10, go ahead and take a look at the input current of the forward converter. You see that the shape is like this. It's instead of flat zero, it's actually a negative current back to the source, right? That happens because of the magnetizing inductance. And as I said earlier, keep the two plots away from each other, basically. Right? Don't allow them to overlap. Right? Okay, so that's a very long discussion on 1 hour, almost 1 hour and 30 minutes on stability on the filter, which I believe is very important because that's a new topic for every single one of you, right? You didn't think before that filter can actually affect stability, but now you do, right? Now you know it could, right? If not, then let's move on to the next topic, power factor correction. Another circuit that we may introduce to the input side of the DC to DC converter or power supply would be power factor corrections, right? So what is power factor? First of all, with purely sinusoidal waveforms, the power factor is the cosine of the angle between the current voltage and the current, right? So cosine of theta V minus theta I, right? So this only is true for sine wave, right? So don't use this if the waveform is not sine wave, right? The more general equation for power factor is not this, right? This is only unique for sine waves. But the one that always works for power factor is this, right? P over S. The ratio of average power to apparent power, right? So this equation works for any type of waveforms, any type of circuits, linear, nonlinear, sinusoidal, non-sinusoidal. This equation works, right? So be careful, okay? This one only works for sine wave, right? Then power factor may be leading or lagging, or could also be unity power factor. When unity power factor, the load looks like it's a purely resistive load to the source, right? And the basic concept of power factor is usually depicted by, for example, this power factor triangle, right? Where you have the watts, right? The real power on the x-axis, the reactive on the y-axis, and the hypotenuse is the apparent power, right? And the angle right here is called power factor angle. That determines the value of the power factor, right? Cosine of theta, right? But again, for non-sinusoidal, you use P over S, right? Instead of cosine of theta. Why correcting power factor to unity? Improve system efficiency, since the less the power factor, the more current is required from the system to deliver the same wattage, right? So if let's say again, I'm looking at a power triangle, oops, right here, just use the example we have in our house, for example, right? Let's say one of our loads in the house is drawing P and Q, right, that way. Then the apparent power will be the hypotenuse, call it S1, and S1 is equal to V1 RMS times I1 RMS, right? And let's call this Q1, right? Now for call it P1, Q1, and S1, right? So for Q1, you can see the power factor here, right? If let's say it is sinusoidal, right? Let's just stick with sinusoidal for now. Yeah, you can see that power factor 1 is equal to cosine of theta 1, right there, right? Now I could get the same power. I could get the same power P1 with smaller angle, right? If I do this, for example, right? If let's say I was able to get less Q, right, for the same power, the same watts, but Q now is less, then that corresponds to our new S2, which is equal to V2 I2 RMS, right? And theta is going to be theta 2. So power factor 2 is equal to cosine of theta 2. And we know because this is a cosine function, power factor 2 will be larger than power factor 1, right? So basically this improves, right? Improved power factor. Agree? So what is the benefit of doing this? Well, in our house, for example, which one is, well, anytime you using the power, you plug it to the wall, right? And when you plug it to the wall, which of the two here will be considered constant? Voltage or current? Anybody?
Voltage.
Voltage, right? So voltage is pretty much around 120 volt RMS, right? Right. So S2 will be also V2 times I2, but V2 is equal to I2. Sorry, V2 is equal to V1, right? So therefore, right, if let's say I've just put in 120 volts right there, right? S1 is equal to 120 volts, right? Oops, yeah, 120 volts RMS times I1 RMS. S2, the same voltage, right? 120 volts times I2, right there, right? Which one is bigger, S1 or S2? You can see clearly the hypotenuse of S1 is longer than S2, right? So therefore, since S1 is larger than S2, that means what? That means I1 is larger than I2. Okay, so hopefully this proves to you one benefit of improving power factor. Right? If I'm able to reduce Q for the same wattage, then the amount of current required, right, from the wall plug, right, from the source to power the same wattage is going to be less, right? I2 is going to be less than I1, right? So that's good overall, right? Because your load requires less current from the source, right? And the source, this current comes from power plant, right? And imagine if this current is big, right? It's coming from so many houses. so many customers. This load corresponds to losses, right, across, or this current, I should say, represent losses across transmission lines, right? So if you can reduce the amount of current, right, then the loss across the transmission line will also be reduced, right? And keep in mind that the loss across the transmission lines or distribution lines is equal to I squared times R, right? It's proportional to the square of the current, right? So if you can somehow reduce the amount of current by a factor of 2, then you can save energy by a factor of, save power loss by a factor of 4, right? That's how important power factor correction is. Any question on that? That's one benefit of improving power factor, right? Another benefit would be harmonics, right? In EE427, we talked about the effect of um, power factor to harmonics, right? We have what we call distortion power factor versus displacement power factor, right? Displacement is the one that you get from theta v minus theta I. Distortion is when you get from harmonics, right? So if you can somehow improve the distortion power factor, then you could also improve the overall power factor of the system, right? Less current required for the same amount of watts. Right? And another reason would be we need to improve power factor to meet regulations. More than 30% of electronic products in the world market are now covered by government regulations limiting the total harmonic distortions of their input line current. And total harmonic distortions affects power factor, right? This affects power factor. So therefore, if you can improve power factor, then it'd be good, right? Because then it would meet the regulation covered by regulation imposed by the government, right? Just about anything that is line powered, from laptop adapters to desktop computers, appliances, and servers, are covered from under 100 watts to multi-kilowatts. So these are all regulations that restrict us from having certain amount of THDs, which is again affecting power factor. The most recent regulations are from China, known as the China Compulsory Certificate, which joins the existing regulation from Europe, IEC 1003-2, and Japan, GICC 6100. The European Union put also another regulation right there into effect to establish limits on harmonics of the AC input current, right? Basically limiting power factor as well. Right? So harmonics and power factor go along, right, hand in hand, right? If you have a lot of harmonics, then your power factor is going to be very low. If you have less harmonics, the power factor is going to be high. Devices required to pass the rigorous Class D emission limits are personal computers, personal computer monitors, and television receivers. Other devices were only required to pass the relaxed Class A emission limits. And I have some examples of Class A, Class B, Class C, Class D. I'll let you read through this yourself. And I have some also look like I have the plots for the regulations, for the two regulations, Class A and Class B, for the two classes. Class A, as you can see right here, right, that's the amount of emission, right, that is allowed. That's red right here belongs to FCC regulation. The dash line, right here, the green dash line, that belongs to European standard, QP. I don't know what QP is. And then there's another standard right here from European standard, the same standard, but it's different categories, looks like, right? So you can see the blue is more restrictive than the green, right? And FCC is more relaxed on the higher frequencies compared to the European counterpart, but it's actually more stringent to this one right there, which is also a European standard. And this is class what? What is this? Class B, right? Class B is even more restrictive, right? As you can see, for FCC, that's what we need to follow here, right? FCC, noise level, and European standard. Right? Again, those two same ones, QP and AV. I wish I knew what they are, but I unfortunately don't know what QP stands for and AV stands for. Anybody knows maybe? But you can see the QP is less stringent than the AV, right? At higher frequencies for class B, FCC is more stringent than the counterpart from Europe. And just to give you an idea that when it comes to real products, right, actual products, you have to meet these requirements, right? And how do you meet these requirements? Like less emission, well, filters as well as power factor, right? Improve power factor. Okay. Any questions on this? Issues with SMPS, switching mode power supply. Well, if you do have power supply, typically the input is AC, but the output is DC. The load requires DC, so then you have to have AC to DC in between, right? And AC to DC is typically done by a full bridge rectifier, just like this, right? And then there is a problem because we talked about this in EE410, right? Because the output of this rectifier, if it's not filtered, it will be something like this, right? So this is what you'll be seeing at this node if there is no capacitor, right? That's a bad DC, right? And so you have to have what do you call it? A very good DC to DC controller to regulate the output voltage into a flat output voltage that has small ripple, right? Or you can improve this output voltage, right? Instead of having big peak-to-peak ripple like this, right? Imagine if it's 120 volts RMS in, that's around 170 volt peak, right? So that peak-to-peak ripple there from here to here, that's pretty much 170 volts peak-to-peak ripple that goes into our DC to DC converter. That's not good, right? So what we can do here, we can clean up the output voltage of the rectifier. How? By connecting capacitor across the output of the bridge. If you do that, then the output voltage, instead of looking like that, it would be looking like this, actually, right here, right? Like that. So much better DC to send into, to deliver into our DC to DC converter, right? But there's always a trade-off, right? There's always a trade-off of doing this, of doing anything. On one side, you improve the DC quality of the DC voltage coming out of the rectifier by simply putting the capacitor at the cost of input power factor, right? Without any capacitor, the input current here would be sine wave, would be a pure sine wave, right? If there is no capacitor. But now, again, when there is no capacitor, the output side looks very bad. That's bad, right? But the input side looks very good. But as soon as you try to improve the output, right, by putting a capacitor, right? So now the DC output is good, is better, but then the cost of it would be much worse input, right? So the input current will look like this, pulsating current. And of course, that would produce a low power factor, right? If the input voltage is still sine waves, right? But then the input current looks like this, like that, then you can see how bad it is, right, in terms of the power factor, right? So you have the displacement power factor, theta V minus theta I. If this is the current, this is the voltage, right? And you also have the harmonics, right? Distortion power factor, right? Because the shape of the current is no longer a sine wave. So you got hit by two different power factor, displacement power factor and distortion power factor, right? So now by adding capacitor, the input becomes bad, the output becomes good, right? So it's always a trade-off here. Right? Now, why is that the input current looks like this, right? And that could be explained from this picture right here, right? Let me erase first. The reason being the capacitor holds some charge, right? As soon as you put in a capacitor, then of course capacitor holds charges, right? So right here, this node cannot go to zero anymore, right? It cannot go to zero anymore, right? Because capacitor would hold that charge. So therefore, right, that node now would have some voltage, minimum voltage, right? So if there's a minimum voltage, that means if you think about this, if you are the diode right here, right? How does a diode conduct? A diode conducts when its anode is more positive and its cathode, right? VA is more positive than V cathode, right? So if the node right here, right, the voltage at that node looks like this, whereas the input voltage, the anode, that's, you see this node right there, that's the same as the cathode voltage, right? That's the same as the cathode voltage of the diode. Look at the anode of the diode. The anode follows the source voltage, right? So source voltage is a sine wave, right? So therefore, a sine wave goes like this, right? Then up again, right? So you can see clearly from here that the diode will not be on all the time. Right? Some time, you can see this is VA. The anode voltage is less than the cathode voltage. The blue is less than the red. If that's the case, then of course diode will turn off. Right? That's why you see this current right here. Right? This is at the output. Okay. At the input, of course, it's going to be AC, so it's going to be the mirror image of this. Right. So you can see right here. Right. This is when, for example, between here and here, but anode voltage is higher than cathode voltage, and if you zoom in, right, if you zoom in, this is what's going to happen. Something like this. Right, so that's the sine, that's the input, P in sine wave, right? That's the capacitor voltage, right? That's the capacitor voltage. Okay, so that's why at this node, at this point, for example, not node, sorry, at that point, since sine wave is larger than capacitor voltage, anode is larger than cathode, diode conducts, right, through this current. See, this current tells me that the diode conducts. Until when? Until, you see this point right there? Sine wave is less than capacitor voltage, right? So at that point right here, the anode is less than V cathode. That's why diode turns off, right? And it keeps turning off until the next time anode is larger than cathode, right? So that's why at the input, this current is reflected back and it gives you this shape right there, right? Ugly shape of input current gives you very low power factor, as low as 0.6, I believe. Right? Any question on that? Those of you who took 410, this is the second time you've seen this. Right? All right. So then how do we correct the power factor? Now, it's not like you correct the power factor as you would in 212, right? In 212, E212, for example, when you have a lagging power factor, right? That's what we have here is a lagging power factor, right? By the way, if you look back to this picture, it's a lagging power factor, isn't it? Current is lagging the voltage by that much angle. So current is actually lagging. There's a lagging power factor. And in E212, we learned that if you have a lagging power factor, that you need to put capacitor, right, to compensate. But that's not the case here. Why not? People who took 410, this is only true, right, if you have a lagging power factor, lagging, right? Lagging power factor. Yes, you put capacitor for what kind of circuit? Anybody? Start from L. So you can apply, you can use capacitor to correct lagging power factor if the circuit is a L and then I. Anybody? If I give you the third letter, then you would know. Still no?
Is it a linear circuit?
Yes, very good. Linear circuit. Yes. So that's what you learn in EE212, right? You learn about AC circuit, which are all linear circuits, right? Only has capacitor, inductors. There's no switching. What we have right now is a switching circuit. Switching circuit is a non-linear circuit, right? So therefore, if the power factor is lagging here for non-linear circuit, then you cannot do this, right? That's no longer working with capacitor, right? So what you do here is to what's interesting is that we use switching circuit, right? The switching circuit, I should say, the switching circuit causes this problem, right? Causes the power factor problem. So now it comes full circle because the way we fix this power factor from a switching circuit is by using another switching circuit. Right? Instead of a capacitor, we put another switching circuit. Right? So lagging, not good. Let's introduce the switching circuit, which is another nonlinear circuit. Right? There. So this is switching. This is also switching. Right? So switching creates the problem, but now switching also solves the problem. Right? Is that cool? Cool. Comes full circle. Right? It comes full circle now. And one way to correct the power factor is by using boost power factor corrections, right? So boost converter is what we use. And I'm running out of time, but basically what we have here is that we are introducing, do I have a diagram here somewhere? Yes, right here. Yeah. So instead of just a pure capacitor to correct it, right? You have a boost power factor correction. That's a boost converter right here, right? And I'll explain this on Wednesday on how a boost converter actually corrects power factor. But that's basically what we have right now. We replace the capacitor with a boost converter, right there. Now, right away we recognize that there could be an issue here, right? Because a boost converter is a step-up converter, isn't it? Imagine if this is 120 volts RMS, right? That's 170 volt peak. So over here, we're not filtering the voltage. So from here to here, right? That's 170 volt peak. Oh, sorry, peak. But yet we are stepping it up, see that, because it's a step up converter. So here is actually a much larger voltage than that. I would say around 400 volts, right? DC. Because you get 170 volts and you step it up to 400 volt DC. Right? But also, the thing about boost converter is that it can accept a wider range of input, right? So that would make this even worse because the input voltage in Asian countries, right, is not 120 volts. It's 220, right? So what is the peak on that one? Times √2. So now if you put 220 at √2 into the input of the boost, then imagine the output voltage that you're getting here is even higher, right? So maybe this could be as high as 600 volts, right, at the output. That's a very high voltage, right? Relatively speaking, of course. For a power supply, it is a high voltage. So that's one, I would say, trade-off of having a boost converter. It will do the job in correcting the power factor, but at the cost of higher voltage at the output. Why is that a disadvantage? Anybody? Why is having a high voltage here not good? Anybody? Then we can adjourn. Any guess why having a high voltage at this node is not good? Or with the converter, right? The entire converter is seeing high voltage. Why is that not good?
Any higher rated components, which
Well,
are more
very good.
expensive.
Very good. You got the answer. Very good. Exactly. So more expensive components, right? Because higher voltage components are expensive, right? You have to have higher voltage MOSFET. See that Q right there? It's MOSFET. That's going to be high voltage MOSFET, right? Diode is high voltage, right? Capacitor is going to be high voltage, right? So all of the stuff that you see in the power stage of the boost would be high voltage. So very good. That's the answer. Right? Making not only that it's expensive, but also safety, right? Safety issues is there as well. Higher voltage means dangerous, right? Dangerous voltage to work with. Okay, and then from here, from high voltage, we actually stepping it down, right, to 15 volts or 12 volts or 3.3 volts, right? So now we have a big ratio between the output of a boost to the actual output voltage that we use for our loads, right? Well, that's another problem right there in terms of efficiency, right? Okay.